Welcome. In this video, we're going to talk about a particular code. Now, everywhere you look, you find codes. If you look at your student ID, that number on your student ID is coded. If you have a credit card, the credit card number is also part of a code. In this video, we're going to look at the ISBN code in two types. There's an ISBN that has 10 digits and an ISBN 13. And the common question with all of these codes that are out there is, how good are they? Can they correct lots of errors or just a little bit? Can they do any error correction at all? Maybe they can just do detection. Can they deal with the switch bug? That's what we're going to discuss here. In particular, we're going to put the ISBN 10 up against the ISBN 13 in a little bit of a battle. We'll see which is better in which situation. So if you take almost any published book or magazine, you flip it over, on the back, you'll see an ISBN number. Sometimes you'll see the ISBN 10 and sometimes the ISBN 13, and sometimes you'll even see both. So the short of it is they introduced the ISBN 10 to keep information about books. The very last digit is a check digit, so it's not any information about the book itself. And at some point, we wanted more digits to describe this, so the ISBN 13 was introduced. So we're going to go through an example putting together the details about the ISBN 10 versus the 13. So first, the 10. The 10-digit International Standard Book Number, or ISBN 10, was introduced in 1970. The first 9 digits are called information digits, so these are all information digits. Well, the 10th digit is chosen so that this equation below is 0 in Mod 11. So keep that in mind. We're using Mod 11, and you pick the J so that all of this stuff here, let's say all of this stuff here is summing up to 1. You'd add J as 10 to make sure that you'd get 0 in Mod 11. Now there is one sort of nuance about this. Sometimes that last digit can't be a number. It's not always X, but whenever you get J as 10 in Mod 11, then instead of putting a 1, 0 right here, because we want to just use 10 symbols, mathematicians refuse to pick anything other than X, so we put an X there. So the standard question for all of these codes, the most exciting thing to find out if you're thinking about the digit error, is what is the minimum Hamming distance for the ISBN 10? So let's try to think about what that would be. So when we're thinking about the minimum Hamming distance, let's try to think about how close can code words be. Let's try to make two code words as close together as we can possibly think of them being together. How about we just start with something straightforward to look at? Let's say we'll make A, B, C, all of these letters, we'll make them all zeros, and then we'll think about what the J would have to be. So my ISBN 10 as an example has its information digits as all zeros. Then let's think about what that last digit would be. Well, if all of this sums up to 0, then J would also have to be 0 in Mod 11. So here we've written down a possible ISBN code word. I imagine that this code word, or ISBN 10 number, is not actually attached to any book because it's all zeros. I don't know that for a fact, but it's nice for this discussion when we're trying to pick two code words that are close together. So how about we take the very first digit and we'll just change it into a 1, and we'll make all the other digits a 0. And we're not talking about an error here. I want to try to build another valid code word, another valid ISBN 10 number. So let's think about what that last digit would be. If this A is 1, then you have 10, and then 0, 0, 0 all the way. So you have 10 for all of that part, and then the J, well, that J would have to be 1. Okay, so what is the minimum Hamming distance of these two code words? Let's call them X and y. So we can simply say that, the Hamming distance, maybe not the minimum just yet, but the Hamming distance of x and y is equal to 2. There's 2 differences between those 2 code words. Okay, so what does that tell us about the minimum Hamming distance? It tells us that the minimum Hamming distance is either 2 or less. So let's think about why. Our minimum Hamming distance cannot be 3, for example, because we already found 2 code words that are just 2 apart. The minimum Hamming distance is the closest that they can possibly get together. So if we've already found 2 as the distance between 2 possible code words that we just randomly thought of, then the minimum must be less than or equal to 2. And we're searching for the minimum here. So what should we do next? How about we think about what if the minimum Hamming distance was equal to 1 and whether that's a possibility or not. So let's assume that the minimum Hamming distance is equal to 1. Then that means that we can find a code word and another code word that have a distance of 1 apart. So let's write out these 2 code words in terms of this congruence. Okay, so we're supposing that our first code word has letters A, B, C, and so on, and the second code word also has those letters. But we're saying that x1 and x2 differ in one place. So I guess we can choose where that place is. Like, let's say, for example, it could be A. So maybe the A down here has to be an A prime. But that's certainly not the only choice for the A prime. It could be a different possibility as well. The B could have the prime on it, or the C, or for that matter, any other letter that's sitting there. Maybe it's the F. It's just there's one difference. All the other letters are the same. So the A is the same, the B is the same, C is the same, so on and so on and so on, except for one difference. And they're both congruent to 0 in Mod 11. So if we were to compare these 2 congruences to each other, they would of course be congruent because they're both congruent to 0. And then from here, we could cancel out 10A on both sides of the congruence, 9B on both sides of the incongruence, and so on. We can cancel everything out except for the 5F and 5F prime. So what we would be left with would be 5F congruent to 5F prime. Just focusing in on this part here. Everything else cancels out. So from here, let's think about this congruence. Because we're working in Mod 11, and 5 is relatively prime to 11, we can use the cancellation law. We can cancel out the 5 on both sides of this congruence. And what we're left with is F is congruent to F prime. But that was supposed to be the one digit that we picked to be different. And we knew that there would be one digit that's different than the other code word's digit because we forced ourselves to assume that the minimum Hamming distance was 1, and we picked a code word that had that Hamming distance of 1 with another code word. So this would mean that all the digits that we were looking at are in fact the same. So in other words, if you try to pick 2 code words that are just 1 apart, you won't have success. We have a contradiction here. So that means that the minimum Hamming distance cannot be 1 between these code words. Now, to fill in the gaps in this proof, we have to consider the other possibilities as well. We didn't have to pick F. We could have picked 6E instead of 5F. So let's clean up our argument a little bit by being a bit more general. We'll pick a general coefficient and a random letter that goes with that coefficient. So I've picked C, as my coefficient and z as my digit from the code word. So c is just one of these coefficients, and if it would happen to be 7, that could be the c value, and then whatever digit here is from my code word, I've called that z. So c can be any value from 1, 2, all the way up to 10, and z can be any digit. Okay, so there's all the possible values of c, and it would correspond to possible values of z. And remember here, x just simply represents the digit 10 with one symbol. So we have this congruence set up below, and this is the real important one to look at when you're thinking about a Hamming distance of 1. And again, the cancellation law will apply because, kindly enough, 11 is a prime number and c ranges from 1 to 10. So all of those numbers have inverses in mod 11 and they can all be canceled out. So we get that z is congruent to z prime. But when z is congruent to z prime, it means that all the symbols in the code word x1 and the code word x2 are exactly the same. So that would mean that the Hamming distance between x1 and x2 is actually equal to 0, and that forms a contradiction. So we'll give that the lightning bolt, and that concludes that we cannot have a minimum Hamming distance of 1 in a more general proof to write down on our page. But this is the key equation to look at here. When you're asking, is it possible for just one of these to be different, then you can just focus in on one of those and decide that it's impossible for just one of them to be different. So we've now discovered that the minimum Hamming distance cannot be 1, it can never be 0, so that the minimum Hamming distance must actually equal 2. So now that we have our minimum Hamming distance, it becomes really quick to find out how many errors we can detect and how many we can correct. So remembering back to the previous video, the number for detection was n plus 1, n being the number of errors. So what we want to do is compare that to the minimum Hamming distance and say, okay, we can detect one error. N is equal to 1. And how many errors can we correct? The magic number for correction is 2 times the number of errors plus 1 has to equal 2, the minimum Hamming distance. But this equation is not possible to solve, so we can't correct any errors. So the right answer here is none. So no correction can be done with the ISBN 10, but we can detect one error. So if you're typing in an ISBN 10 to, let's say, Amazon, and you make a single digit error in your typing, you are not going to be directed to the wrong book. You would be directed to maybe a message that says you have typed in an incorrect ISBN number, please try again, as one possibility. Okay, so now let's move on to the ISBN 13. So this one was introduced in 2007, and the way it's encoded is a little bit different. So first notice that they do this in mod 10 as opposed to mod 11. Now I didn't make up this congruence that's sitting here in front of us. This was something that I looked up and seen how the ISBN 13 is officially encoded. So let's delve into that a little bit more. So they take all of the digits, and every odd digit in the code is added together, and every even digit in the code is multiplied by 3, and then we add up the total, and we make sure that we get 0 in mod 10. So the final digit in the ISBN 13 is, of course, the 13th digit. So we're going to call that X sub 13. And that is the check digit that would be over here on this side of the summation that is chosen so that we get 0 in mod 10. So again, we're interested in what the minimum Hamming distance is. Let's see how close we can stick two code words together. So again, we'll start with all zeros as a possible ISBN 13, at least theoretically, it's good for this exercise. And then we'll change the very first digit to a 1, and we'll make all the other information digits a 0. All the way up to the end, I want you to pause the video for a moment and think about what digit has to go right there if we're going to make a valid ISBN 13 code word. Okay, so hopefully you had a chance to think about that. So if you thought about how all of these digits here are 0, all the even position digits, the second position, the fourth position, the sixth position, they're all 0, so all of that's 0. And these digits just get added together. Most of them are 0. The first one's 1, and then the last digit must be a 9 to make sure that we get a grand total of 0 in mod 10. So these two code words, let's call them X and Y, give us a Hamming distance of 2. So the Hamming distance of X and Y is equal to 2, and that means that the minimum that the Hamming distance could possibly be, so the smallest h of xy that we could possibly find, has to be less than or equal to the number 2. It's either 2 or 1 at this point. So let's think about, well, what if the minimum Hamming distance is 1? We'll try to disprove that. So if we can find the minimum Hamming distance of 1, then we'll look at the one digit that differs between the two code words. Let's say it's xi and xi prime. So C would be either 1 or 3 in this case, because that's the coefficients that we have, either a coefficient of 1 or a coefficient of 3. And the xi could be any digit from 0 all the way up to 9. Okay, so from here, we can go ahead and use the cancellation law. The C cancels out on both sides because C is either 1 or 3, and in mod 10, those numbers are relatively prime with 10. So xi is congruent to xi prime. So this means that we in fact don't have a Hamming distance of 1 between the two code words. So it is impossible to pick two code words that are that close together. And the minimum Hamming distance is equal to 2. So let's write that down. Therefore, the minimum h of x, y is equal to 2. So from here, we can again discover how many digits we can detect and correct. It's really similar to before. How many can we detect? Well, 1, because we compare it with n plus 1 equal to the number 2, which is the minimum Hamming distance. So we can detect 1 error, and the number that we need for correction is 2n plus 1, and we'd need to make that equal to the number 2, and that's impossible, so there are no errors that can be corrected. So we can't do any error correction with the ISBN 13, at least for the digit error. So our next question is about the switch bug. Can the ISBN 13 deal with the switch bug? So let's focus in on the part of the code where the switch might occur. Like for example, let's take x1 plus 3x2. And what's happening is the x1 and the x2 are switching place. So as a result, you would get x2 plus 3x1. What we want to know is this change, so this amount here, is this when it changes to this amount, is it detectable in mod 10? In other words, detectable would be like if something changed by 4, you would be able to see that in mod 10. But if something changes by like 10 or 20 or minus 10, it's not going to affect the truth of the congruence. In that sense, you don't detect it. So what I'd like to do here is take a difference between these two expressions. If we take that difference, then we're going to think about, is it possible for this difference to be 0 in mod 10? So taking the difference, we get 2x2 minus 2x1. So is it possible for that result to be 0 in mod 10? Well, it certainly is, because 2 times 5, for example, is 0 in mod 10. So if you take any example that has x2 and x1 differing by 5, you're going to notice that the ISBN 13 cannot detect the switch bug. So to do this proof, let's just prove it by a counterexample. Let's throw something at the ISBN 13 that it just can't deal with. Okay, so let's try to think of something simple like 0 and 5. It's not going to be able to detect this. So we'll just make all zeros so our calculation is as easy as possible. So what would go in this very last spot? What's our check digit this time around? So if you think it through, this 5 here would get multiplied by 3, and we would get 15 in total. So we would need a 5 at the very end. But now let's suppose these two digits here got switched. So you have 5, 0, and then a bunch of zeros for the rest of your code word. Now the question is, did we detect this error? We started with a valid code word, and then we did a switch. And then if all systems are working, this should no longer be a valid code word in the ISBN 13 code. But if we calculate this, we have 5 and then a bunch of zeros and then a 5 at the end, we get 10, which is 0 in mod 10. So this is also a valid code word. But an error detection system should change a valid code word into an invalid code word. But we have an example where this just didn't happen. We have an example where we didn't detect the switch bug. So when we say, can we detect the switch bug, we mean always. Mathematicians don't want, sometimes we'll detect it and sometimes we don't. The ISBN 13 is not good enough to detect the switch bug because we have one example that slips through the error detection system. So my answer here is no. What about the ISBN 10? Can the ISBN 10 detect the switch bug? Let's try the same type of thing. So again, let's focus in on the part that the switch can occur. So let's say we have 10a plus 9b, and we think about, well, maybe the a switches with the b, for example. Then we would have 10b plus 9a after the switch. Let's think about the difference between these two expressions. What we would get is a minus b. And we'll think about, can that be 0 in mod 11? Is it possible for that to be congruent to 0 mod 11? Now let's remember that these two digits, a and b, that swap positions, a is not equal to b. They're different digits. So if a and b are different digits, you're never going to get 0 in mod 11. This is going to lead to a successful detection of the switch bug. Let's write a formal proof of this. Okay, so we'll start by saying, say that A switches with B. Now, of course, other switches could occur, but they'll all be symmetric with this switch because the coefficients of A and B have a difference of 1, and that's the same for every other pair in the ISBN 10. The difference of the coefficients will always be 1. So let's look at the code word. So we've got 10B after the swap, and 9A, and then 8C, and then so on and so on and so on, all the way down to J. Now this particular expression that we just wrote out has the switch occurring, and what we like to have happen to make sure that we detect the switch bug is we want this expression to no longer be congruent to 0. We're saying, okay, something bad has happened, the A and the B is switched, and we want to know that it's no longer 0 by plugging in all of these letters into this expression. So we do know some things about the first two terms in the expression, this part here, the 10B plus 9A. 10B plus 9A. It's also written here, 10B plus 9A. We know that when we compared it to 10A plus 9B, we didn't get 0. So that means that this amount here compared to this amount in mod 11 must be different. So if we think about making that exchange below, we're going to get something different out of the deal if we exchange what's in the brackets for the 10A plus 9B. And then the rest of it all stays the same, 8C, and then ... all the way down to the check digit, which is J. Now all of this stuff here, we always pick J so that this expression is 0 in mod 11. So if we read back what we have, we now know that after the switch occurs, we get something that's not congruent to 0 in mod 11. And that's exactly what we want to have happen for successfully detecting the switch bug, which the ISBN 10 can do. So the answer to that question is yes. There's one more type of error that we're going to discuss in this video. This one I've called the smudged digit error. So in this scenario, what you have is some digits being sent away, and then during the transmission, the explosion here is that one of the digits has its information lost. But you do know as the receiver which digit it is. So I think of it like, there's a finger that came in and smudged that part away, and we lost that information. So in terms of error detecting, that's obvious. As soon as you look at it, you see something that is not even a symbol that you would ever use, so there's something bizarre or smudged away, or there's something missing right away. It's like if I read a sentence out loud, and then all of a sudden in the middle of the sentence, I missed a word. You would detect that immediately. But the question is here, can we do correction when the location is known? So can the ISBN 10 correct the smudged digit error? So what we have to do is go back to the equation that calculates the check digit for the ISBN 10. Okay, so here's my ISBN 10 code, and what we're asking is, can you solve for any one of these letters? If one of these letters goes missing, can you recover it? So what we could do, for example, if D was missing, we could move all the other terms to the other side of the congruence, multiply both sides by the multiplicative inverse of 7, and then finally solve for D. So the answer to this question is yes, we can solve for any one of the variables above. Okay, so what about the ISBN 13? So same thing there. We want to know if we can correct the smudged digit error. So let's check to see what that code looks like. Okay, so let's think about this code. If you wanted to solve for a variable over here, you don't have to solve for two at a time, but any one of the variables here, you could certainly move all these terms to the other side of the congruence, and all of the terms here that you know to the other side of the congruence, and you solve for one of the x sub i's when the I is odd. Or over here, you do something similar. Move all the other terms to this side of the congruence, and then multiply both sides by the multiplicative inverse of 3 in mod 10. And that's 7. So that would give you a way of solving for any one of these variables. So again, the answer is yes, we can deal with the smudged digit error. Okay, so let's put this into action. So here's an example of a ISBN code word that has a smudged digit error. So this digit here has been smudged away. Our job is to find it. So try to do this. See if you can do this for the ISBN 10 and the ISBN 13 below. Try to solve for the missing digit. Okay, so I'll do the calculation now. So just so I don't make any errors, I'm going to rate the coefficients above each of the numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. And then as I go through, I'll reduce in mod 11. So 3 times 10 is 30, and I'll think of multiples of 3. So 30 is the same as minus 3. 9 times 6 is 54. That's 1 less than 55. 8 times 3 is 24. That's 2 more than 22. For my variable, I'll just use y, so 7y. In the next one, I have 2 times 6, so 12. 1 more than 11. And then I have 5 times 2, so 10, or minus 1. 4 times 4 is 16, which is 5 more than 11. 3 times 2 is 6. 2 times 6 is 12, which is 1 more than 11. And 4 times 1, of course, is 4. So we want to add all of these together so that we get 0 in mod 11. And I'm going to look for a quick way to kind of calculate these so it's not so hard on myself. I'll look for all of the 11s that I can find. So 5 and 6, that's congruent to 0 because that's 11. And 1 and minus 1 is sitting right there. So what's left? There's a 4 plus a 1 plus a 2. That makes 7 minus 4. So I have 3 in total. So there's 3 plus 7y. We want all of that to be congruent to 0 in mod 11. So we'll subtract 3 from both sides. So we get a minus 3 on the right-hand side. And all we have to do left is invert 7. So how about we think of multiples of 7? So 7, 14, 21. Okay, 21, there's a hit. 21 is 1 less than 22. So that would bring me to minus 1. So I want to get to positive 1. So I'm going to multiply both sides by minus 3 to give me 9 as my final answer. Okay, so let's try the same idea, but for the ISBN 13. So let's give this a try. Okay, so let's calculate through this one as well. So to make sure I don't make mistakes, I'm again going to put a little 3 over top of each of the even positions and calculate from there in mod 10. So I'm going to reduce as much as I can. I'm going to change the 9 into -1. And I'll use y for my variable again, so 3y. I'll change the 8 into -2. I'll change the 3 times 3, 9 into -1. And then +6. And then 9 again, so -1. -1 for 9. And then +6, +2, +12, or just +2 to reduce in mod 10. And then +2. And then 3 times 6 is 18, so I'll write -2 for that one, and then a -1 at the very end. So let's look for ways that we can reduce nicely in mod 10. So how about 6 + 2 + 2? That's congruent to 0 in mod 10. Or here we have a 2 - 2, so that just goes away. That's also congruent to 0. And let's count up what's left. We've got -1, 2, 3, 4, 5, 6, 7, +6. So -7 + 6 is -1. So this line is congruent to, we have -1 + 3y, and we want to solve for y, so that is all 0 in mod 10. So this implies that 3y is congruent to 1, and if we multiply both sides by 7, we get y is congruent to 7. So that is our answer. That's our missing digit. Thanks so much for listening, and we'll see you on the next one.